Hi everyone. So today we're going to be talking about graphing polynomial functions. And so let's start with just basically talking about a couple of key vocabulary words before we get into the actual graphs themselves. So a polynomial function, as we've seen in the previous lesson, is a function where we're basically adding up a bunch of monomials. And we put it in standard form if it goes from the largest degree all the way to the smallest degree, ending with whatever the constant term is. Now, a sub n, which is right here in this general form of a polynomial, this is called the leading coefficient. And so the leading coefficient is basically just the number in front of the term with the largest degree. In this case, it's nth degree, right? X to the n. Okay, so let's look at some examples. If I have f of x equals negative x cubed minus x squared plus 8x plus 1, the degree, remember, is the largest exponent. So this is degree 3. We also called this a cubic in the last lesson. And the leading coefficient is the number in front of the term with the largest degree. And technically, there's a -1 in front of that x cubed. Notice you're just taking the number in front of it, not the variable. Okay, go ahead and try those next two. Okay, and then we'll go through it together. So negative 5x plus 1. This is technically degree 1. It's a linear. And then the leading coefficient would just be -5. It's the number in front of the term with the largest degree. Okay, next one, we have 12x squared minus 11x plus 31. This one is degree 2. It's a quadratic. And the number in front of the x squared term would be our leading coefficient, which is 12. Okay, so just like in our whole unit where we've had the most basic form of every type of function, we call those parent functions. We have parent functions for each of these different polynomials: a constant, a linear, quadratic, cubic, quartic, and quintic. So what we're going to do is quickly sketch what each of these look like. So if it's constant, it looks like y equals c. Well, we've seen these before. This would basically just be like a horizontal line, just like that. Okay, the next one, we have a linear. Actually, let's use function notation. So instead, let's write that as f of x equals c. Okay, I'm going to go ahead and use a different color too, because I think it'll show up a little bit better. Okay, linear is degree 1. So if we write that, it would be written as f of x equals x. Well, this is just a line with a slope of 1 and a y-intercept of 0. So it looks something like that. Okay. All right, a quadratic. This would be f of x equals x squared. And so we know what this looks like. This is a U-shaped curve, and its vertex would be at 0, 0. Looks just like that. Okay, the cubic, this one might be a little bit more on the new side. F of x equals x cubed. So it kind of looks like a parabola on that side, but then it goes down. We actually call this opposite end behavior, where one end goes up, the other end goes down, and we'll talk a little bit more in detail. Quartic would be f of x equals x to the 4th, and it actually kind of looks like a parabola, but it's slightly wider in the center. So it looks something like that. Okay, and then your quintic, no surprises, f of x equals x to the 5th is actually going to look a lot like the cubic, but a little bit wider in the center. Okay, so you might notice all of the graphs on the right-hand side, those are all odd degrees, and they have opposite end behavior. So one end of the graph is pointing up to positive infinity. The other end of the graph is pointing down to negative infinity. If you look on the left column, those are all even degree. Notice the end behavior on either side is the same. They both point up. So it turns out it has to do with the degree of the polynomial, whether it's even or odd, with that end behavior. Okay, so let's go ahead and talk about some characteristics and how to find end behavior. So before we get to those examples, if we have a positive leading coefficient and an even degree, that's kind of like what we had in the x squared and x to the fourth example. Notice both ends are pointing up. Well, it turns out for an even degree, you could also have both ends point down. And then notice the odd degree, it's opposite end behavior. So we'll use that to help us kind of fill in the chart in a little bit. But first, it says using your graphing calculator, determine the end behavior of the following functions. So what I'm going to have you guys do at this point, go ahead and take your Chromebooks out. We're going to go to Desmos. And we're going to go ahead and type in that polynomial. So let's see, the first one is 4x to the fourth plus 6x cubed minus x. And notice this one, both ends are pointing up. So as x approaches positive infinity, we're going up to positive infinity. And even to the left, as x approaches negative infinity, we're going up to positive infinity. So it would be infinity, infinity. Okay, go ahead and do that for numbers 2, 3, and 4. Pause here. When you're done, go ahead and unpause and we'll do them together. Okay, so for number 2, we have negative x squared plus x. So I'm going to go ahead and type that in. Negative x squared plus x. Notice both ends are pointing down to negative infinity. So as x approaches infinity, f of x approaches negative infinity. And as x approaches negative infinity, f of x also approaches negative infinity. Notice 1 and 2, those are both even degrees with the same end behavior. All right, number 3, we have 2x cubed. So let's go ahead and type that in, 2x cubed. It looks like as x approaches infinity, we're going up to positive infinity. And as x approaches negative infinity, we're going down to negative infinity. Oops. So infinity, negative infinity. All right, last one, we have negative x cubed. Type that in real quick. Notice it just flip-flopped, right? So as x approaches infinity, as we move to the right, we're going down to negative infinity this time. And then as x approaches negative infinity, as we move to the left, we're going up to positive infinity. So it's just flip-flopped. Okay, using this, let's go ahead and draw in the end behavior. So if we have a positive leading coefficient and an even degree, that's like in example 1, both ends point up to positive infinity, okay? But if we have an even degree and a negative coefficient, that's like in number 2, both ends are going to point down. Okay. Number 3, if you have a positive leading coefficient and an odd degree, to the right it points up, and to the left it points down. And then finally, number 4 was our example of a negative leading coefficient and an odd degree. To the right, it points down, and to the left, it points up. And then it does something in the middle, but that's kind of what the edges of the graph look like. Okay, let's move on to numbers 5 and 6. These are examples. So looking at these graphs, do they have an even or an odd degree? And is the leading coefficient positive or negative? Well, in number 5, both ends are pointing down. So this is going to be an even degree, but it's going to have a negative, leading coefficient. Okay. All right, number 6, to the right, it's pointing up, and to the left, it's pointing down. So that means this is actually going to be an odd degree because it's opposite end behavior. And now it looks like just because the right is going up and the left is going down, it's going to have a positive leading coefficient. Okay, now we have what's called turning points in the graph. And turning points are basically where the graph changes direction. So it changes from either increasing to decreasing or from decreasing to increasing. And you can notice on this graph, it creates these little bumps. So if we change from increasing to decreasing, this guy right here is called a relative maximum. It peaks, right? So if the turning point is higher than any nearby point, it's called a relative maximum. Now over here, you notice down here, it changes actually from decreasing to increasing. And so that right here is called a relative minimum. And so if the turning point is lower than any nearby point, it's called a relative minimum. The maximum and minimum values are called relative extrema. Turning points define where the function is increasing and decreasing, just like we kind of wrote down on our diagram. Okay, so now what we're going to do is we're going to try to put all of this together and do a little bit of graphing. So let's take a look. And actually, first thing we're going to do, we're not going to graph on the graphing calculators. We're going to just use Desmos for this. It's a little more user-friendly. So we're going to go ahead and graph x cubed minus 6x squared plus 7x plus 2. So we're going to do, let's see, x cubed, let me look at mine on my other thing. There we go, minus 6x squared. Okay, plus 7x. And then plus 2. And we're going to go ahead and use Desmos to identify our relative maximum and minimum. So it does look like we do have a relative maximum at the point approximately 0.709, 4.303. Oops, 4.303, whoops. Make sure you have the x and the y coordinate. The relative minimum is at about 3.291, negative 4.303. Okay, now, increasing intervals. We want to figure out where the graph is increasing versus decreasing. Remember, it changes at each of the relative maximums and minimums. And when you want to tell your reader where a graph is increasing, what we're looking for, because we're tracing along the x-axis from left to right, we want to give x values. So tracing the graph, notice it's increasing, starting off this way to the left, negative infinity. So it's increasing from negative infinity, but then it stops when it hits that peak right up here. It stops when it gets to about 0.709. Now, looking back at the graph, it looks like it actually starts increasing again after 3.291. So it's going to be union 3.291, and then it's just going to keep increasing to infinity. Now, where it's decreasing is right in between the maximum and the minimum. So from 0.709, notice I trace my graph, my finger will go down until I hit 3.291. So 0.709 to 3.291. Okay, so the next thing that we're going to do is we're going to put all of these pieces together. We're going to graph some polynomial functions and then state some of the key features. So we're going to use a table to help us do that. So number one, we have negative x cubed plus 3x squared, and we're going to go ahead and start by making a table. Now, one thing to note is we actually already know what the end behavior is going to be because we have an odd degree and a negative leading coefficient. And so looking at our chart, you can actually go back to our notes. If it's an odd degree and a negative leading coefficient, to the right, it's going to go down. To the left, it's going to come up. So if you graph this correctly, it should look, to the right, it's going down. To the left, it's coming up. And it's going to do something in between, probably to connect. We don't really know, but that's what our table is going to help us determine. Okay, so let's go ahead and pick some values, -3, -2, -1, 0, 1, 2, and 3. Okay, so we're going to plug these values in. Here's a little trick to help you do this in your calculator. So let's use our actual calculator this time because what we want to do this is get you prepped for like a quiz or a test. You're going to just have a regular calculator. Okay, so it's negative parentheses. I'm going to go ahead and plug in -3 first. So -3 parentheses cubed. So use the little caret cubed. And then we do plus 3 parentheses times -3. And this is being squared. And then you hit enter. Okay, so we get 54. And we're going to add that to our table. All right, so then we have -2 that we're going to plug in. Instead of typing this all out again, here's what you can do. Hit the up arrow until it highlights the part we typed in and hit enter. Notice it copied it. Well, instead of -3, I just want -2 to be in the parentheses instead. So you can hit delete and just replace the 3's with 2's, and it will give you the next value of your table, which is 20. All right, next we want to do -1. So you can do the same thing. Up twice, hit enter, replace the 2's with 1's. Note this only works if you make sure you put parentheses in there. All right, looks like we get 4. So I'm going to go ahead and put that there. Whoops. 4. This one's easy. 0. We get 0 because 0 plus 0 is 0. 1 we could do probably in our heads too. So it would be -1 plus 3 is 2. 2 is not too bad either, but we can do it in our calculator if you want. Up to you. We're just replacing the -1's with a 2 instead. Oops. And we get, it looks like 4 again. Okay. 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 And then let's see, the last one we're plugging in is 3. Oops. And we get 0, it looks like. Okay. All right, so we're going to use that table to go ahead and help us graph. So I'm going to scale. It looks like I can scale by ones. It's just telling you that that 20 and 54 output, it's just going up to positive infinity. I think scaling by ones is perfectly fine for this one. I'll show you what I mean by that in a second. Okay, so we're going to plot these points. We have -1, 4. We have 0, 0. We have 1, 2. We have 2, 4. We have 3, 0. Okay, so polynomials, they are smooth and continuous. So when you're actually connecting these dots, you kind of just want to make sure that they are smooth and there's no sharp turns. Notice I didn't do like a jagged edge like that. It's smooth and continuous. Now we also know the end behavior. To the left, it's going up to positive infinity, and to the right, it's going down to negative infinity. And so we can fill in that end behavior. Just make that a little nicer. Okay. You could probably plug in 4 and just make it slightly more accurate, but this is pretty darn close. All right, domain, tracing from left to right. It looks like we're going from negative infinity to positive infinity. Range, we're going from bottom to top. This is also negative infinity to positive infinity. Relative maximums, it looks like there's one right here. We're not going to be able to get this exact, but it's about 2, 4, it looks like. Relative minimum looks like it's right here at 0, 0. We already know the end behavior. As x approaches infinity, we're going down to negative infinity, just like right here. As x approaches negative infinity, we're going up to positive infinity. Increasing intervals. So it looks like it's only increasing in this middle section right here. And remember, we use x values, so that would be from 0 to 2. Decreasing, remember it's where my finger goes down as I trace from left to right, would be from negative infinity. It stops decreasing at that minimum, so to 0, but then it starts decreasing again after 2 all the way to infinity. Okay, so that is the step-by-step how to graph a polynomial using a table. Go ahead and do number 2. To check your work, go ahead and go to my website, mrsfitzmath.com. All you have to do for this one, make a table, plot your points, use your calculator to get the table values, and then state all your key features. All right, thank you for watching, and have a great rest of your day.